Hey everybody! So here's our first kind of e-learning video. So we're gonna see how this goes. I'd recommend just taking notes in your notebook, kind of like you normally would in class. Label it, put the date at the top, partial fraction decomposition day 1 video. You'll want your calculator for this as well. And so we're gonna get started here with a little warm-up on the top left. I'm gonna zoom in and we'll get going. Part of the whole idea here is for partial fraction decomposition, it's basically the reverse of getting a common denominator. So you've taken something like this before and gotten a common denominator, so take a second, pause the video if you need to, and let's get a common denominator here. All right, so this is what we get, and typically we'd probably leave it in factored form on the bottom, but what I wanted to show you is the process of partial fraction decomposition is actually going to be going from this answer, where we would start the problem, and we're going to try to get back to the original, where it's separated into two separate fractions. And so what you might notice is, like, okay, the two separate fractions, the denominators are the two factors of our 2x squared minus 3x minus 2. But where does the 1 and the 2 come from? It's not clear that it would come from the 4x minus 3. So it's going to be our job to figure out where does that 1 and where does that 2 come from? How do we solve for that in order to split up this fraction into two separate fractions? So to be able to do this, we're going to talk about 4 different cases that we'll see. And I'm going to put the kind of formulas up on our screen right now. Let's see, there. So essentially we're looking at, in our original fraction, what's the format of the denominator. Okay, and so the format, we're going to always be looking in factored form, and we're going to look for, are our factors linear terms or are our factors quadratic? And we add this little word irreducible. It's not, I guess it's not a little word. It's a irreducible quadratic means it can't be factored, because if it could be factored, then it would really just be linear. So we have, in each of those categories, linear and quadratic, we have distinct and repeated. So let's focus in on distinct for a second, or linear distinct. So when we have linear distinct, we have some polynomial on top and distinct terms, meaning they're all different. So I have ax plus b, cx plus d, ex plus f. Right? So the format that we're going to use is we're going to split it up into fractions with each of those linear factors on the bottom and a unique constant on the top, and we use capital letters for those. So I have capital A over ax plus b plus capital B over cx plus d plus capital C over ex plus f, and continuing that on. So when the factors are linear, we actually get constants on the top of each separate fraction. Let's zoom out here and then look at what if the factors are repeated linear factors. In this case, again, we have a polynomial on the top, and we have some factor that's linear, ax plus b, repeated. So maybe it's to the second, or to the third, or to the fourth, in this case to the nth. And so in that case, we sort of have to build up to whatever that power is. So I have a over ax plus b plus capital B, so a new constant on the top, over ax plus b squared, and then to the third, all the way up until we get to the nth. And that's how we would deal with a repeated linear factor. Then we can talk about irreducible quadratics. And the pattern is sort of the same. The only difference is that when we have irreducible quadratic factors in the denominator, we end up with linear terms on the top of each separate fraction. So I have these factors in the bottom. They cannot be factored any further, but they're quadratic. So I get ax plus b with capital letters over the first quadratic plus cx plus d over the second quadratic, and we would continue that on. If the quadratic irreducible is repeated to the nth power, we have the same kind of idea as the linear repeated ones. We have to build up to that power. So ax plus b over ax squared plus bx plus c. Then we get a new linear term on the top, capital Cx plus d, over the quadratic to the second power. Then we'd have maybe ex plus f over to the third, all the way build that up. Okay. So today's examples are going to focus on distinct. And I think that by doing a couple examples, I know this might not make a whole lot of sense right now. Do a couple examples, we'll see where it's going. So we're going to start with example 1 here. So the process we're going to go through here to solve this problem is actually to split it up using the kind of format we just went over, and then solve for those variables. In this case, it'll be a and b, by setting the original fraction equal to the new fraction. And so let's show you what I'm talking about. So I split this up. I've got x squared plus x minus 6 in the numerator, or the denominator, and that can factor into x, and then what, plus 3 minus 2. So I have non-repeated linear factors in the bottom, or distinct linear factors. So to split this up, I'm going to have a over the first one, x plus 3, plus b over the second one, x minus 2. And so what I'm really going to get here is, on the left side, I still have x minus 7 over, and I'll write it in factored form, x plus 3, x minus 2. And on the right, I'm going to get common denominators, but just involving a and b. So if I were to get a common denominator here, I know it would be x plus 3, x minus 2. And on the top, I'd have to multiply a by x minus 2, and I'd have to multiply b by x plus 3, just like we did in the warm-up. And so I create this situation where, well, the denominators are equal to each other. They're the same exact thing. So in order for this fraction on the left to be equal to the fraction on the right, the numerators have to be equal. So I can basically ignore the denominators now and deal only with the numerators. So I have on the left x minus 7 equals, and on the right, I'm going to distribute this out. So I get, what is that, ax minus 2a plus bx plus 3b. And what I want to end up doing is matching up my coefficients. So I have x terms and I have constant terms on the right. And I have an x term and a constant term on the left. So I'm going to actually write the left as 1x minus 7 equals, and I have ax and bx. So I can factor out x from there, and I get a plus b times x. Another way of thinking that is you're just combining the like terms. If I had like 2x and 3x, we'd make it 5x. You'd add the 2 and the 3. So I'm just adding the a and the b. And then I also have plus my constant terms, the ones that don't have x. So that's going to be plus a negative 2a plus 3b. And now to solve this, it's actually kind of cool. We have this expression, 1x minus 7 equal to something x plus something. Well, those coefficients have to be equal. Something x plus something. The 1 right here has to equal the coefficient on this side. So I end up being able to write an equation where I match up the coefficients. So I get that a plus b, the coefficient of x, has to be 1. And I also get that negative 2a plus 3b has to be equal to the constant, negative 7. And now I just have a system. So I'm going to speed this up and solve this system pretty quickly, but if you need to pause it, do that. All right, so all that work there tells me that A is equal to 2 and B is equal to -1. And so I can finally go back and essentially write my final answer using that initial setup way at the top here. So I get that this partial fraction, x minus 7 over x squared plus x minus 6, is going to be equal to A, so 2 over x plus 3, plus B is -1 over x minus 2. That's my answer. You could also write it as minus in the middle and then 1 over x minus 2. So let's try another couple problems here. One other thing we'll see here is that when we get to the point with a system, we can use our calculators. We can use the reduced row echelon form, the augmented matrix that we were doing earlier in this chapter 10 to help us do that more quickly. All right, so let's go over to example 2. Now, in the interest of not making this video way too long, I'm gonna talk through it with a lot of it written out already, so make sure you pause it or rewind it whenever you need to. All right, so the first few steps are factoring the denominator, and it's a cubic, so the first thing you're thinking is maybe I can factor by grouping, and you can. You end up with x plus 1, x minus 1, and x plus 2 is the 3 factors. So they're all different linear factors, so we're going to split it up just distinct linear. So it's a over x plus 1, b over x minus 1, and c over x plus 2. So we want to write this out like this, where you've got our fraction original on the left in factored form equals split up on the right. Then we're going to multiply the a, b, and c by what they're missing. So we end up with a common denominator, and we can ignore the denominators. So we get 5x plus 7 is equal to a times the x minus 1, x plus 2, b times the x plus 2, x plus 1, and c times the x plus 1, x minus 1. And then I need to distribute each of those out so that I have a quadratic in each of those spots. And when you do that work, we end up with 5x plus 7 equals, and all of this. So our job right now, just like the last problem, what we want to end up being able to do is to match up the coefficients. I know I've got some x squareds, I've got some x's, I've got some constants on the right, and on the left, I know I have 5x plus 7. So my job is to find all the coefficients. Okay. And instead of distributing each of these out and then combining all like if that's going to take forever. So what we do is we go on a little coefficient hunt. And so what I want you to do is set up this as the next line. We know we're going to have stuff times x squared plus stuff times x plus stuff as the constant. So let's go on that hunt. Let's find all the x squareds. All my x squareds are there, there, and there. Which means, what are the coefficients? Well, I would have a, b, and c, based on distributing in each of those parentheses. Then I need to look for my x terms. X, and I don't have one in the third parenthesis. So I collect those coefficients. I'd have ax in the first one. I'd have b times 3x, so my coefficient of x would be 3b, and I don't have any coefficient in the third. Then when I look at my constants, I'd have negative 2a. From the middle, I'd have 2b, and in the third, I'd have minus c. So we get this situation where I have 5x plus 7 equals all those. So now I know I can match up the coefficients. My x squared coefficient on the left is 0. So I can write an equation, a plus b plus c equals 0. And then for the x terms, I know the coefficient of x has to be 5, so I get a plus 3b equals 5. And then my constants have to equal 7. So we get this system, we've got a, b, and c, my 3 unknowns. I have 3 equations, so I'm going to use good old augmented form of a matrix. I haven't done that in a little bit. And use reduced Echelon form. So you would set up your augmented matrix like this and put it in your calculator, and when we do all that, we get that a is -1, b is 2, and c is also -1. So to write our answer, we go back to that original, fraction up there and make sure we match it up correctly. So we get -1 over x plus 1 plus 2 over x minus 1 plus -1 over x plus 2. So for example 3, to make it go quickly, I've got it all here. The biggest difference here, when we factor, we get an irreducible quadratic, x times x squared plus 4. So to split this up into our partial fractions, we have both a linear and an irreducible quadratic. So I do a over x for the linear piece plus bx plus c over the x squared plus 4 for the quadratic piece. So we kind of mix and match whatever linear terms you have, those get a regular a, whatever quadratic factors gets the bx plus c, or so on. So we go through that whole process of getting the common denominator and then matching up, going on a little coefficient hunt. Be careful because here we have x times the bx is really bx squared, so that's why the b is with x squared. And this time when we match up our coefficients, we get actually some pretty easy equations and end up with 24 equals 4a, so we can get a is 6, c is already -2, b ends up being 5, and that's how we end up with our final answer of 6 over x plus 5x minus 2 over x squared plus 4. So we've had 3 examples there. The homework are problems similar to that, and also just sort of setting up like the first 3 problems or 4 problems are just set it up to this step here with the a's, the b's, and the c's. You don't have to solve that at all. All right, thank you for watching.